The next section is about future tools and materials. And our first speaker is Fabian Strunden. He is a coding designer and electronic enthusiast. Originally from Germany, he went to secondary school in Sligo and then went on to college to NCAD, and now works for the Dublin-based design lead company DAQRI. Fabian is motivated by the belief that technology helps us to reduce redundant tasks and then allows us to focus on the beautiful aspects of life. Please welcome Fabian on stage.
Thank you very much. Great. I think we have the... Perfect. So I'm Fabian Strunden, UX UI design lead at DAQRI. And today I'm going to be talking about designing for augmented reality. I hope everyone had an experience of augmented reality before, but maybe if not, you should definitely try it out in the future. So I've always been fascinated with mechanics and electronics. One of my first inventions was a pulley system that allowed me to close the curtains from a bed from across the room, and I came up with it at the age around 10. And the reason why I call this an invention is because I came up with something where I didn't need any instructions on how to do so, or I didn't reuse a kit that was existing that was instructing me how to do that. I love that as humans, we have the potential of ideating tools and mechanisms that simplify our lives. And along the way, we experience joy and actually a satisfaction. I've graduated from product design from the National College of Art and Design. During my studies, I've learned how to design physical products, services, but most importantly, how to emphasize with people. Understanding the needs, pain points, and motivations of the others is essential when innovating new technologies. At DAQRI, we invent every single day. We are operating in a realm that is vastly unexplored and has the potential of changing the way we work, travel, and live our lives. We have offices of specialized focus areas across America and Europe, with the European headquarters in Dublin, in the Docklands in Dublin. We are providers of core augmented reality technology like computer vision and hardware, and we combine those to create amazing products. So over here we have the DAQRI Smart Helmet and the DAQRI Smart Glasses, both of which are augmented reality wearables that are already used today in real work appliances, primarily in industrial applications. The DAQRI Smart Helmet protects the worker while also allowing him to see work instruction, data visualizations directly in the field of view of the worker. The DAQRI Smart Glasses are primarily used in lean manufacturing, but accomplish the same goals. The Smart HUD is an augmented reality holographic head-up display for automotives. What I enjoy about working at DAQRI is that our focus is not creating a flashy demo or creating something cool to look at. We are creating real industrial use cases. We develop industrial-grade AR, focusing on enterprise markets that have large value gain, allowing them to champion this revolutionary technology. With the help of our wearables, people can do their daily work faster and safer. Or alternatively, do entirely new tasks, following augmented reality instructions that contextually guide the worker. Here we see someone wearing the smart glasses, and in their field of view, they see these inspection points, so they would be guided from one to the next with orientational guidance, and they're instructed to turn a lever, inspect a valve or a gouge, and then capture that information directly in the smart glasses. When a worker gets stuck or needs assistance, they can call a remote expert. Here we can see a remote expert calling directly into the field of view of the worker. So me wearing the glasses, I would see the worker, I would see some instructions that the worker can put into my field of view, as well as instructions there that they can draw into my field of view. So they have the possibility to annotate my vision in real time, providing instructions from anywhere in the world. Additionally, they can also share documents into our field of view. meaning that if I need an electrical plan or some instruction, I can follow a guide that they share with me, so meaning that I don't have to take all the documentation I could potentially need on a servicing job with me. Thermographer is a prime example of where we redefine of what is currently humanly possible. We create high-resolution 3D models directly by passively capturing information when you're wearing a wearable. We create photorealistic RGB models by using that mesh that we create passively in the glasses and applying the camera information on top of it. We also have thermo overlay, so someone with a helmet can see real heat vision when walking around an industrial plant. We're going to show you a video now that is going to show this in a bit more detail. So on the bottom we can see the field of view of the worker. So components that are running hot in a factory can be detected over time by passively tracking through the glasses that are worn by the worker. As well as levers that have been chained and have been unnoticed. So augmented reality is really an ongoing revolution, and we are investing a lot of time into designing the ideal user interactions. Let me introduce you to the fundamental building blocks that we use to build augmented reality applications. Designing UIs for augmented reality is different from designing UIs for mobile or desktop screens. Here you can see an example. For once, color does not translate well from our screens onto the augmented reality lenses. Our lenses add light to the light that is coming in from the real world. The additive color mixing means that the color black is fully transparent, where white should only be used sparingly as it occludes the environment. The user can, if we have a full block of white color in front of our eyes, it can be compared into looking into really bright light, and we want to avoid that at all costs, obviously. So over here we can see the example of just colored rectangles on the top transitioning from white to fully black. In the row below, we're showing that of how that would be experienced on the AR device, where we start at white and then completely go into transparent. So this is this additive filtering. Also, other colors here, these colors would be at full opacity, but we can see that white will always come through from the back, and even stronger in blue and red. Secondly, with two lenses, our devices provide stereo vision. We have the option of placing UI content anywhere around the user in the 3D environment. But virtual objects should only be placed between 0.5 meter and 20 meters from the user. Placing content closer to 0.5 meter can cause eye strain and discomfort for the user. If the virtual content is played further than that, we stop perceiving the stereo separation, meaning that we're not clear anymore how far this object is actually away from us. Also, describing measurements in pixels becomes meaningless in 3D space. We talk about button dimensions in millimeters. This is a really big change in talking about graphic design or UI design, because the way we usually communicate has to completely change. Our layers helps us to take advantage of 3D space while still supporting an intuitive and familiar UI. So here we can see that UI items can come out of the UI and come towards us. While this is very difficult to present in a 2D presentation as we're experiencing it here, if you're wearing the glasses, you can see that you can see minor distance differences in items coming through and closer to the user. And with that, we can create very kind of powerful user interactions with very good feedback. On the left here, I think it's a bit washed out on this projector, unfortunately, but it shows a layer system that we use to create the language around at what distance from the user specific UI elements should be positioned. The navigation, for example, the navigation button, for example, is 65 millimeters by 65 millimeters and positioned at the distance of 2 meters from the user. I think that gives you kind of an idea of how we communicate about these UI components. So, getting the user experience right when superimposing virtual content into the physical environment is a really big challenge. The users are moving around, making them the directors of the AR scene. Placing content into the appropriate content space is essential when designing a successful augmented reality application. The user needs to remain aware of moving cranes, colleagues, passing vehicles, as well as having easy access to the augmented reality content. So this gives you an idea. We have a top-down view on the user here, and we are indicating the field of view of the user. So that content here is 2 meters placed away from the user, and we define the space around the user by 3 content spaces. We have the world space. World space is something that's dropped into the environment, just like this table, and the user has the opportunity to move around that while that content still stays static, locked in the world. This is fantastic if we have multiple users wanting to have a communication about a single object together. Then we have the body space. Body space here is content that is set at a certain distance from you. If we move away from the content will follow you back into your field of view. Otherwise, you would lose it, right? You wouldn't want to have content that kind of moves but is stuck behind you and not in your field of view. So that's why we have this follow behavior that brings it back to the edge of your field of view to not occlude your environment. And then we have the HUD notifications. HUD notifications is what we use for battery warnings as well as volume controls. And they are actually static. So they're within your field of view, and when you move, they will come with you. The reticle is our prime means of interaction in augmented reality. It's positioned in the center of the field of view, and it behaves similar to the mouse pointer. But with one essential drawback, we don't have a physical trigger to perform the click. To support hands-free UI interaction, really important in our industrial use cases, the reticle performs a click after a short time delay. Our engagements with customers have allowed us to experiment and learn how to design and build successful AR applications. Here you can see a range of the environments that we engage in. I want to show the gas turbine servicing application in closer detail. So this is one of the customer engagements that I've closely worked on. This is a gas turbine. It is a huge piece of equipment, and it is installed with millimeter precision. The value of one of these is immense, so to expand the life expectancy of one of these is key. The process of learning how to service one of these is not easy, and it takes about 3 years for a technician to service by themselves. Many of the technicians are mechanical engineers, making them already very experienced within that realm. So giving them instructions is kind of a hard, difficult subject to do. As a large multinational company, Siemens invests into improving their processes. We were asked, can AR make this training of service technicians better? To prove that AR can successfully train a maintenance technician, we picked one key servicing task, being the assembly of a gas burner. You can see a single gas burner being built into them on a ring around the whole gas turbine. This is where the fuel is injected and burned to spin the shaft, which is connected to a generator which puts out electricity from the plant. Now, the design experience is crucial. Augmented reality is a very visual experience, and therefore, the early involvement of the designer is key to the success of the final application. As Jeff Powers mentioned earlier, experimentation sparks new outcomes. And this is exactly what we do as well in the design team. So we sell the vision from a very early stage. The designers are involved to actually make it possible for our clients to understand what we're actually offering to them, right? Because it's a very abstract concept of saying, we have this device, now we're going to build you something that will revolutionize your inspection or assembly experience. So then we go and shadow the workers. So we fly out to the workers and we actually work with them. We emphasize on like, how do they do their task? What are their pain points? What are the little tricks on how to get through their workday faster? What do they like? What don't they like? Why do they like procrastinating at times potentially? And we need to answer those through our applications as well. So then we design and prototype, and we do this in a very physical way. So sometimes we build huge props to be able to reflect of what we see on site in our office out of cardboard, and then build augmented reality applications around that. I often build SketchUp models just to familiarize myself with the environment as well. And these are very crude and simple, but they still are able to visualize what we're designing for me and the rest of the team. And then when we give the application to our client, we don't just like let them have it. We fly out again and we train those technicians so they are fully instructed. And this is because they're dealing with something that is very new, and them being acceptant of what we're introducing to them is absolute key to the success of the application in the field and to just the feedback to our company as well. So for the gas burner application, we have broken the UI into 3 UI components. All right, well, we have KPIs that we design against. And these are really what are motivating us to be true to the design rules as well. So most importantly, our applications have to be safe, comfortable, and efficient. Amount of required head motion is key to reduce that, right? If we're placing content all around the worker and they have to move more for getting the UI content than to actually do their task, we're failing at providing efficient application. The rate of errors. The application should help the worker to reduce errors and is most importantly not add any new errors by the UI that we're providing. The time on task can be hugely reduced with our applications by providing really informational instructions in situ of what the worker is really working on. And the amount of obstructed field of view means your field of view is what you're seeing around you through our glasses. If we are starting to obstruct that, there's loads of dangers that the worker is exposed to. So we need to come up with very clever solutions of keeping content out of the field of view, but very easily accessible. And then, super. So here's our 3 components. We have the work instructions on the right here. This is the whole list. So we would have translated the work instructions that we get from paper-written work instructions into a UI that is usable and reflective of what the worker is used to, as well as providing new functionality. Then we have the 3D viewer. The 3D viewer is something that they just have never experienced before. This means that they can drop the work instructions and the 3D viewer next to the assembly, right? So we're assembling a burner here. You can see it in the picture. The burner is around this size, and it's in a big wooden box, and components are lifted with a crane into the box. The 3D viewer is positioned next to it and gives step-by-step instructions with animations that are guiding the user on what parts to line up, where to insert the right bolts, in very, very easily interpretable animations. And on the top, we have the Smart Guide. The Smart Guide comes with the worker, right? So these 2 components are dropped into world space, what I've mentioned earlier. And then the Smart Guide comes with us in body space. So it's always in our field of view. That way we can control the application, add photos captured from the device to that specific work instruction step. So then we conduct studies. From an engagement, we write a case study that evaluates the suitability of augmented reality in the industrial training environment. So we have grouped the users into these three types, which is the novice, the refresher, and the expert. What you can see here is that the expert takes 40 minutes to complete the application. A novice who has never done this task before takes 45 minutes to complete this application of building a gas turbine, a burner. Isn't that incredible to just be able to enable people to do something that they weren't able to do before in the same or nearly the same time as the expert who has done this many times before? So originally a novice user would have taken 480 minutes to complete this. And that would take a lot of kind of in-classroom training on the day, as well as just having to go forth and back between paper-written manuals, back to the task, potentially even losing the slides, etc. So there's loads of potential of just extending that time. Where now with the smart helmet, the information is coming with you, right? We don't have to go somewhere else anymore to find the information. It's with us, and it's contextual, meaning that we always adopt the information to be suitable for the exact specific moment and the environment that the user is within. So after the user assembled the burner, we asked them to complete a system usability scale to evaluate the success and potential adoption of the application in the everyday work environment. The system usability scale consists of 10 questions, and the user answers by selecting from the range of strongly agree to strongly disagree. The questions include, I think that I would like to use this system frequently. I found the system unnecessarily complex. I think that I would need to support of a technical person to be able to use this system. So these are example questions, 3 example questions out of the 10. As we know, new disruptive technologies are often met with resistance and skepticism, especially in environments where things have been done that way for a long time. The expert who already knows how to do the task was still able to see the benefits, right? So the expert is on the top here, and the end user supported, and this is end user supported adoption of the expert. And then we have the management-driven adoption. This is where we don't want to be when introducing new technology into an environment. And then we have the refresher. And they are end-user-driven adoption, meaning that they become now stakeholders of this, right? They're going to be driving this. And this is incredible, and the same for the novice. So they were really happy. So someone who already knows how to do the task, who was told something they already know, they're still supporting this. But someone who has never done, so who is really gaining the value from what we have offered, you can see that they're huge supporters of this. What are the key takeaways? So typically it takes a day to complete the first assembly versus 45 minutes with AR. Regarding efficiency, I love the quote which we have captured here from one of the workers. Humans are very visual. If I can interact with the drawings in 3D like this, it makes understanding them a lot easier, especially if I have to deal with new components that I have never built before. Right? And this is exactly that point where we're saying we're bringing someone into a new task and all of a sudden enabling them to do that. And then we have the confidence, which is like novices felt empowered and safe when using the app to complete the assembly. And the error reduction, no user made any error in assembly using the app. And that is incredible, right? When reading papers, the amount of times you open the wrong page, read the wrong talk value, because everything is just adjusted to that specific step, we can really avoid errors by using this. So thank you for joining today. And if you have any questions, please reach out at any point. I hope I made AR understandable for you guys. And looking forward to hearing questions.